All right, good morning. Welcome to MFC Group's FasTech Seminar series hosted by FH Sales. Thank you for joining us this morning. Today we're spotlighting From Cells to Shipping, your battery pack decision guide with Zeus battery products. Our speakers for this seminar are Gina Galante and Peter Foret. Gina is a seasoned business development manager at Zeus, where she leads sales and marketing efforts across North America, both for standard off-the-shelf and custom battery solutions. Peter is the chief technology engineer with Zeus, where he helps drive the latest battery technologies and educating Zeus customers. This morning, everyone is muted, so please type any questions that you may have into the chat. We'll be happy to answer those, and at the end, we'll open it up for Q&A, and I'll allow everyone to use their microphones at that time. And then after the Q&A, I hope you'll stick around for a fun round of trivia. And with that, I will turn it over to Gina and Peter.
Thank you, Amanda. Give me 1 second here.
Thank you, Amanda.
Okay. Hopefully you can see my screen. Everything look good?
Everything
Perfect.
looks good.
All right. Let me just get this moved. Okay, so welcome everyone. Thank you to the FH team and Mel Foster team for having us today. Peter and I are very excited. So we have some powerful content to share with you and appreciate you giving us your time and, more importantly, your energy. So let's get started. Let's see. So basically, here's how you're going to gain some insight from today's webinar. We're going to start with a quick audience poll to gauge our level of knowledge in the battery pack design world. From there, I'll introduce a few critical concepts like cell selection, chemistry, terms like BMS, capacity, and cycle life, so that we're all working to improve our battery pack foundation. Then we'll shift our energy into options for enclosures, where we will see that there's a lot more happening under the surface than most people realize. Finally, we'll wrap up by reviewing the typical development and certification timelines. This will give you a realistic picture of what to expect for your own projects and how to better support your internal design teams. We want to first here be sure that you're truly plugged into the webinar, right? So let's take a quick moment here. We're going to run an audience poll and try to collect your insight to gain the knowledge of your expertise. So for here, the question that we would like to pull is when it comes to, I cannot see where we're at. Hold on 1 sec. There we go. When it comes to the battery pack design, my expertise level is best described as, I know my battery has a car. I know my car has a battery in it somewhere, and I can tell the difference between a primary and a secondary battery. Or maybe you can say, I can explain the difference between a PCM protection circuit module and a smart BMS battery management system. Or maybe you dream in cell balancing algorithms and wake up thinking about voltage curves. So Amanda and her team will go ahead and do a quick tally, and then we'll return the results to you in just a few moments.
It looks like we have several people who are basic and familiar with some battery types, and then we have a couple who are advanced certified battery nerds.
Awesome. Awesome. All right. Well, great job, everyone. So it's important to conduct these reviews early on in the design timelines to evaluate various cell types that are out there. When selecting the type for peak operating performance, cycle life of the design, and the number of expected cycles needed, as well as upfront investment cost, or the NRE that may be needed in initial development. So let's take a closer look. The Zeus team will often hold a Teams meeting or a quick conference call to pulse a few questions early on to help you and your team work through the selection process. The cell selection that Zeus offers is ultimately driven by the customer's application, the environment for which it will be used in, the number of charge or discharge cycles that are desired, and the time that it may be required to sit on a shelf or sit idle inside of the device. So some key takeaways for selecting cells. The first category is prismatic. You would choose this format for medium to large applications requiring higher volumetric energy density. These are good, think of like EV battery packs. The middle one, you're going to choose a pouch style battery when the weight limit is critical, especially for handheld applications, or when the volumetric energy density is critical. This type of cell is most common in compact devices. In this case, you could think of our cell phones. This cell type needs careful pack design consideration to prevent punctures and allow for normal swelling during charge and discharge cycles. Finally, you would choose a cylindrical can type for durability, more common like standardization for common sizes like an 18650 or a 26650 cell, as well as reliable thermal performance. These are great for applications where mechanical protection is important in more vigorous environments. Now, a broader yet simple side-by-side comparison is just for you to review. I'll go ahead and pause for just a minute while you glance this over. This presentation will be made available for you after the webinar, so if you're anything like me, it's okay to resist the urge to take notes. And then at this point in time, Amanda and her team will open up the mics just for some quick initial questions from the audience. And then Peter, if you would like to add anything to this slide to kind of talk through it, you're more than welcome to.
Sure, absolutely.
Okay, I've allowed everybody's microphone, so if you have any questions, feel free to unmute yourselves or feel free to type in the chat and I could read those off as well.
This slide is also, kind of useful when you go and see customer and they have an application and trying to decide, what type of cell maybe they may be suitable for their product. So it has. You can see, if you go down, the feature set, it's pretty self-explanatory. And as Gina pointed out, cylindrical are more for applications that require a combination of strength, like a physical, mechanical strength, and also durability. Together with prismatics, they're similar, but just with a different construction. And pouches typically just in applications that need a specific shape, fit in a specific shape, and they have maybe a weight limit, constraints. The lowest weight, in the applications that require low weight, the pouch is the way to go. Sometimes the cylindrical cells have many different sizes nowadays, and the cylinder is not a bad thing because it allows for the air to flow around the cylindrical shape, and it does not need really specific tracks, for and spacers for the airflow. Anybody question? We got a quiet crowd today, so still too early? Yeah, I'm on my second cup of coffee, so I'm good.
Perfect. Okay. Well, Amanda, if there are none, I'll go ahead and keep going.
I don't see any in the chat, so we can move forward.
Sounds good. So now that you have an idea on the cell type, the next category for review is selecting a battery chemistry. So at Zeus, our program managers and engineering staff will consider a variety of chemistries for optimal performance throughout the life of the design. Our sales team also will provide you with insight on ballpark estimation, upfront investment costs, or any NRE and timelines for the initial scope of work. Generally speaking, custom battery packs can take approximately 3 to 4 weeks for samples to be produced, and then mass production is often in the 10 to 16 week, depending on the lead time of the selected components of the battery pack. We do have the capability of assembling battery packs here in the US. We are just outside the Chicagoland area, or we can do them overseas at one of our facilities as well. Our design team will determine this based on our tooling, our manufacturing equipment, the ship to location for the customer orders. Basically, we want to reduce the number of times that batteries are going to be shipped to keep those overhead costs lowered as much as possible. Next, we're going to talk about the battery chemistry. One of the first big decisions is choosing between primary cells, which are non-rechargeable, and secondary cells, which are known as rechargeable. Primary cells, think of those as single-use batteries. Once they are depleted, they're done. You cannot recharge them. The easiest one to correlate is to think of an alkaline AA battery in your remote controls or lithium primary cells that you may be using in a smoke detector. They tend to have long shelf life, some of them over 10 years. They deliver high initial energy density. That makes them great for devices that need to sit in storage or that you only use occasionally, where charging just isn't practical. Secondary cells, on the other hand, are rechargeable. These are your lithium ion, lithium polymer, nickel metal hydride, and other chemistries we see in portable medical devices, handheld instruments, AGV, AMR, robotic applications, and electric vehicles. They do cost more upfront and need charging circuitry designed, but over many cycles, they are far more economical and sustainable. When deciding between the two, the real question is, what does your application need? If the device must be ready after years on a shelf or during a supply chain cycle, or if they're going to be used in a remote location without charging access, primary cells are often the winner. If it's a high use, high drain application where the user can recharge regularly, secondary or rechargeable cells are definitely the way to go. And of course, we also have to factor in the operating environment, the size, the weight limits, and any other regulatory or safety requirements that may be done at the top level or device level. Oftentimes, our design wish lists are quite long, so choosing the right cell at the start of the design can save a lot of cost and complexity down the road. When designing a battery pack, the choice between an embedded or external charger depends on factors like convenience, performance, and application needs. Embedded chargers offer user-friendly, all-in-one solutions ideal for portable devices. This ensures that the optimized charging and reduce risk of user error. However, they do add cost, complexity, and can limit the charging speed. External chargers, on the other hand, are better for high power or industrial applications, offering flexibility, easier maintenance, and faster charging capabilities. They simplify the battery design, but often require the users to manage a separate component. Ultimately, your decision depends on the device's use case, its power requirements, and whether modularity or simplicity is more important for your design. Working through our experience, we'd like to share some of the best practices for designers using embedded or external chargers. Allowing for proper matching to the battery pack is essential. So our first tip here is to engage early. This is common whether you're just designing the battery pack or working through the mating charger. So what we ask is that you do partner with FH and Zeus as early as possible in the concept phase. This way we can leverage roadmaps for various cells, design capabilities, and again, as we've mentioned throughout here, take into consideration some of those outside factors like environment, temperature, storage. All of those will be key inputs that our engineering team is going to need to help you. We really need to define the application early on as well. So we're going to need to clarify whether you need a desktop charger, whether or not it's going to require a BMS on the battery for the embedded system, etc. So specifying the battery chemistry and communication protocols like SMBus or I2C is all critical up in the upfront stages so that we can help you in the long term, or basically bring the product to market quickly. There are some challenging timelines that we know that you're faced with, so going through some of these parameters early on will help you. We will, in some cases, specify custom requirements. We will often start with standard or semi-standard designs as a foundation, but we will highlight any unique requirements early that impact your needs, such as size constraints, environmental conditions, and operational standards. Finally, with regards to compliance and certification, we will poll to understand if there is anything known early on. Sometimes it's not vetted out until a little bit later on in the design phase, but this is particularly critical for global deployments. It's important for you to stay close with your own regulatory team and your external validation labs to determine what may be needed for the battery or the charger. Okay, we're going to run a second audience. It's our final audience poll to collect your feedback. So in this case, which statement best fits your understanding of a BMS versus a PCM? First statement is a PCM is just a BMS without the B or the S, right? Or a PCM protects the battery, a BMS manages and monitors it. The third option, a PCM handles basic over and under voltage and current cutoff. A BMS adds balancing, temperature control, and communication. Or finally, I could explain the difference down to the MOSFET, switching logic, and CAN bus data exchange protocols. So the FH team will throw up that and tally some of the results for you.
Sorry, it's processing.
Okay. There we go.
There we
It's coming
go.
through.
Our most popular answer is a PCM protects the battery, a BMS manages and monitors it.
Okay.
We have a couple of other answers also.
Excellent. And so we have a good mix, a good baseline, which is good to see. Okay. So a protection circuit module, also referred to as a PCM, or a battery management system known as a BMS, plays a crucial role in keeping a battery pack safe, efficient, and long-lasting. These components consistently monitor factors such as charge and discharge cycles, ambient and internal temperature, and voltage levels. If any of these parameters go beyond the recommended limits, for example, under voltage or over voltage or extreme temperatures, the BMS will act. It can trigger a warning signal to alert the user, and if necessary, disconnect the battery from the charger or the load to prevent any damage. This smart monitoring is not only to protect the battery, but also extends its life and ensures reliable performance in demanding applications. A BMS can have fuel gauging and communication ports such as I2C, SM bus, and CAN communication. Let's break down a couple differences between a PCM and a BMS since they're often confused. A PCM, or protection circuit module, is essentially a safety gatekeeper. It monitors for critical faults like over voltage, under voltage, overcurrent, or short circuits. And if a limit is crossed, it shuts the pack down to prevent damage. It's a simple, cost-effective, and perfect for low complexity applications. On the other hand, a battery management system goes much further. In addition to all the protections a PCM offers, a BMS continuously monitors voltage, current, temperature, charge cycles, and overall pack health. It can actively balance cells to extend the lifespan, and it often communicates with the external systems via CAN bus, SM bus, or other protocols. This makes it essential for critical applications like medical devices, electric vehicles, telecom backup systems, and industrial power solutions like AGV and AMR for warehouse type applications. In short, a PCM protects and a BMS protects, manages, and communicates, ensuring that the battery operates safely and at peak performance for the long term. We're going to keep the energy going here, and we're going to dive into the options for battery pack enclosures. This table gives you the ability to match the enclosure type to your application's priorities at a very high level. When selecting a battery pack enclosure, the choice really depends on the balance between the need for protection, weight, cost, and the environment. The first option here is PVC heat shrink. We call them soft packs in our industry. It's the simplest and most cost-effective. It's great for compact designs, but it offers the least mechanical and environmental protection. This also has the shortest lead time options as well. Plastic enclosures give you more durability and can be molded with various custom features, though they're not as rugged as a metal enclosure. Metal enclosures provide the highest strength and the best heat dissipation, making these ideal for industrial and very harsh conditions. But on the other hand, they are much heavier and more expensive. Both plastic and metal enclosures will have NRE, upfront costs for tooling, and could potentially take up to 3 months to develop when you take into consideration the 3D modeling, sampling, tooling time, drop testing, or other various agency certifications that may be needed. Finally, potted battery packs are the ultimate for moisture and vibration resistance, yet they cannot be serviced once sealed. Many battery chemistries prohibit being potted or intrinsically safe. We see the most success at Zeus with intrinsically safe using nickel metal hydride cells. And next, the topic of agency certification. When this arises, we know that this is generally very new for you and your design team, and that you guys are not the experts. And that's okay. So please know that Zeus works with all third-party accredited testing facilities like SGS, UL, Intertech, among others. Zeus can provide a series of testing options both at the cell level and the battery pack level for testing. Ultimately, we will always encourage our customers to get involved early with their testing lab. Whatever the product category or certification that you are seeking to obtain at the device level will often have different requirements, both at the cell level and the battery pack level. In addition, depending on where you intend to sell your product, certain countries will have additional safety requirements that need to be taken into consideration early to allow Zeus to make the proper component selections for safety and reliability during testing. Let's take a closer look at your battery compliance roadmap. In this table here, we're showing a quick overview that compares the main safety and compliance standards for battery packs that are most often used. First and foremost, the UN 38.3 is a mandatory transportation test that is done for lithium batteries. The series of 8 different tests ensure that these battery packs can withstand conditions like shock, vibration, and temperature, and extreme temperatures during shipment. It's basically going to emulate what a potential battery or battery pack may undergo if that is shipped via air, ocean, or land. And ultimately, we want to make sure that it is safe for transport. The UL 1642, that focuses on cell level safety, while UL 2054 looks at a complete pack level safety for both rechargeable and non-rechargeable chemistries. IEC 62133 is the global equivalent for rechargeable battery safety and is often required for market access into Europe and Asia. We do see more customers selecting the IEC path just simply because in recent years it's becoming more harmonized, more globally accepted. It does have a little bit shorter lead time and a little bit lower cost than the UL counterparts. Finally, CE with REACH and RoHS covers environmental compliance and product safety for the European markets. For timelines overall, most tests take approximately 6 to 12 weeks to complete the testing. This is the lead time after we build the samples. So in some cases, the lab or certain pieces of equipment will be in use for other tests, and therefore it could be a queue to get into. So please be sure to be mindful of this timeline to help you keep track of your overall project milestones. Together, these certifications form the foundation for safe, compliant, and globally accepted battery solutions. Lithium battery solutions account for approximately 50 to 60% of new designs at this time. As we mentioned earlier, the UN 38.3 is an international transportation test that is mandatory worldwide. It applies to all lithium cells and batteries, whether standalone or shipped in equipment or packaged alongside equipment. This test must be done before they can be shipped by air, sea, rail, or even over the road. The goal for this testing is to ensure that the batteries can withstand the physical and environmental stresses of transportation without leaking, venting, catching fire, or rupturing. The various tests, such as altitude, thermal testing, shock and vibration, short circuit, and impact crush testing. The certification is a pass-fail, so failure means that the battery cannot be shipped, and any alterations to the battery pack will need to be implemented and retested. Thankfully, our Zeus crew works very hard to ensure we will pass this test criteria for our customers. One thing to note is that when designing lithium packs is the overall watt-hour rating. If lithium packs are over 100 watt-hours, the shipments are considered Class 9 hazardous, ultimately meaning higher shipping costs and more paperwork at the time of shipping to declare this as DG or dangerous goods. Not all carriers work with DG. Therefore, it's important to understand your supply cycle and how and where the batteries are going to need to be shipped. We have now completed your journey from safe design to safe delivery, so let's see where your questions will take us. I'll turn it over our time here together with Peter Ferret to help with your specific questions and answers.
We do have one question in the chat, so we can start with that one. What triggers the need for UN 38.3 on packs that are existing OTS more or less?
Well, what triggers is, ultimately just the insurance that the bags are safe to ship. And it doesn't matter if it's off the shelf or not off the shelf. All lithium, as Gina pointed out, all lithium must be tested to UN 38.3. It doesn't matter whether the pack is off the shelf, not off the shelf. Just going to repeat. It is relatively very common test, and it doesn't take too long, but there's expense to it, and that's sometimes bundled as part of the pricing of the package, or oftentimes, just individually priced, and it repeats itself, year after year. So.
And what that does, just to add on to Peter's, is the annual renewals that perhaps that you're considering. That basically is to provide a current set of documents. So in order to ship, oftentimes carriers are going to want to see an MSDS or an SDS, and there are limitations. You can't have a really old MSDS. So what that will do is that with each order or production run that we're building, we will be issuing or providing what's called a UN 38.3 renewal. It's lower cost than the initial, but what it does is it allows us to provide you with current documentation that are required in order to ship it.
Yeah, thank you, Gina. And also I want to add, to it that when we have an initial design and the battery pack or the battery itself is not approved yet for shipping, the samples can still be shipped. It's just more expensive. They are shipped in a specific and a special, like drums, if you may, that allow for a safe shipping of dangerous goods, A9 dangerous goods. So there's no way around it. No way around, the UN 38.3. It is a global requirement.
Doesn't look like we have any other questions right now.
Okay.
But thank you guys for the awesome presentation. As Gina mentioned earlier, we did record this session, and so everyone will receive a link to the recording and the presentation as well. So if after the seminar's over, if you have further questions, then feel free to reach out to me or your FH sales rep, and we'll be happy to get those answered for you. We can loop in Peter and Gina anytime.